When do you say that a coin is, if it is a unbiased coin, so if you plot the probability distribution graph, like you have, when you throw a dice, what does the sample space consist of? 1, 2, 3, 4, 5, 6. You get this. If it's uniform distribution, 1/6. Yes or no? This is uniform distribution. So now you use random. Yeah. So now you can see random. We will see maybe in one of the classes. So you can use this random function. So when you try to do, you have to use random and srandom. I will leave you there to do a little bit more research and figure these things out. Okay, can you try this one? Read random and srandom. I will talk about them, okay, but you are allowed to use srand these functions. No, don't work on your own random function. Just use default random functions. Okay. Now it is. How to plot the result? Find out, Aman. Those are all the things that you need to check now. How do you plot? Similarly, write a program to throw 2 6-faced dice. Okay. Same problem 1 and problem 2. No, you should be able to do within half an hour. You should be, if you leave the plotting aside, you should be able to do it in half an hour. Graph theory is required. No. That graph theory, this is just you use some tool to plot. Last year, I gave this same problem. One of your seniors, he keeps generating the histogram. There is another Python program which keeps reading the histogram generated so far and it plots it. So as the program runs, you see the histogram going up and down and it gets stabilized. So you should try something like that. No, you keep running the program. There is another program which keeps looks at your. He connected it to Python. The program is written in C, but he connected that C program to a Python program. And so as the tossing keeps going, you'll see initially that it's all skewed. As the number of runs increases, it gets stabilized. It's senior, it's secret. Hardik, thank you, Hardik. The son is doing all right. Yeah, first year student. No, he's not there. Yeah, something like that, Druhan. Output of C program goes into text file and Python program reads the text file. Something like that. I don't know how exactly. Yeah, something like that. Okay, it's fun. Problem 3 is interesting. You should look at problem 3. You really would love it. No, you don't count the number of times points in a circle. It's like this, you know, you have a dart, you keep throwing a dart and randomly, and some points fall inside, some outside. You randomly make the points, and some fall inside and some fall outside. How will we count them? Who is a counter? How many in and how many out? That's the problem now. What is the area of a unit circle? This is, let's say if this is a sorry, this is not one. Let's say, yeah, whatever this. Let's take a 2 by 2. Okay, 2 by 2. Okay, so, and then you put a circle here. What is the area of the square for what is the area of the circle area is pi r square, right? Pi r square. R is 1. So you count the number of, so the ratio of area of circle to area of square is equal to pi by 4. So you use this relationship. So that means, you know, you use this to kind of find out what is the value of pi. You get some ratio, right? When you, the using program, so you keep generating some random points, some points will fall out inside, some points will fall out outside, and some inside. And you check that ratio, and get, let's say that ratio after n samples is ln, then after n samples, your estimate of pi is 4 times ln. As the value of n increases, no, the ratio that you get ln will be very close to the actual pi by 4. Does it make sense? If given a point, can you check if it lies in the circle or within the or outside the circle? You can check now. You just have to write an if condition. So 3 problems done. So tomorrow finish 3 problems. Plotting, for the time being, plot, you just generate the data, put it in an Excel file, a Google Sheet. You just put them in a Google Sheet and plot. Generate data, put it in a Google Sheet, plot. Same also here, also generate data, print it on the screen, you output it to some file. No, I don't mean tomorrow or day after tomorrow. It's just that three problems. No, there will be a 4th problem that will be coming here on randomized algorithm for primality testing. Yes, Miller Rabin. Yeah. Okay, 4 problems, 1 day. Okay, max 2 days. Okay. Okay. Shall we move on? So the next problem is you are getting Let's say you have 1 terabyte of data. Okay. Can you fit 1 terabyte of data in your RAM? Or let's say 50 GB of data, 100 GB of data. So if you have to, so this is where this is your data is present here. So you have to bring the data and bring part of the data. Let's say your data, you divide your data into chunks. You bring the first chunk and then you compute the sum. You bring the second chunk and you keep adding the sum, one chunk after another chunk. You can bring it to RAM. This is your RAM. So computing mean is easy, right? So it's just like you bring a chunk, add them up, you bring another chunk, you continue the addition and you do it. So this is all right. So, but accessing disk is very, very expensive. Accessing disk is super expensive. And so it's okay. Now, let's say when we come to variance, this is a formula for variance. So in order to compute the variance, you have to access your data 2 times. That is super expensive. Does it make sense? That you have to make here, you can compute mean in 1 pass. But here we require 2 passes are required to compute variance. 1 pass to compute mean, the second pass to compute xi. Yeah? So there is, I heard last time if you simplified it, you'll get some formula. How do? You don't need 2 passes? So what is the formula? Sigma x square minus mean square. But you need to know the mean, na? You still need 1 pass to get mean, right? So the challenge problem is there a way to approximately, so you can do one thing, we can maintain a running mean. Running mean is the mean of the data that you have looked at so far. Okay, and then so you keep I don't think C, man. So just to think about the logic. Okay, so running mean, you understand what I mean? Like initially for x1, the mean will be x1 only. For x2, you will have an estimate of mean mu1. For x3, you use an estimate of mean mu2. For x4, this is one way of doing it. For x5, so what happens is after, if the data is properly distributed, after some period, so what happens is you in real analysis, if you study mean mu2, mu3, mu4, after some time it converges. If the data has the right properties, it converges. So after some point k, you have a very good approximation of the mean. Does it make sense what I'm saying? It is like this. If we have data, what I'm trying to say is, when you are trying to compute xi minus mu square, why should it converge? If it has the right properties, it should not. There is no necessity for convergence, but if it has the right properties, it will converge. IIT Kanpur, doctor. So let's say mu I is equal to sigma I is equal to 1 to n sigma xi. This is by n. Okay, not I saw. Sorry, mu k. This is mu k. Mu k is equal to So the point is, no, if this data is kind of a good distribution, if it is properly sampled from the distribution, then after limit as k tends to infinity, mu k tends to mu, the actual mu. Are you all with me here? Some kind of idea what I'm trying to say? That is, I'm saying you don't know the mu, so you use the current estimate of mu. So that is what I'm telling, that's all. Okay, think about it. I'm just giving you some hints. It is like this, you don't know the mean. When you start the problem, let's say, when you look at x1, first data point, you don't know the mean. What is the current estimate of mean if you only look at x1? So your first mean estimate mu1 is x1. When you look at x2, what is the current estimate of mean? x1 plus x2 divided by 2. When you look at x3, what is the estimate of mean? x1 plus x2 divided. That's all I'm saying. In this expression of summation, use the latest version of the mean. If you keep going like this, mu k is equal to sigma I is equal to 1 to n xi minus mu k square. In other words, what I'm telling is, you use this expression sigma I is equal to 1 to n xi minus mu I whole square divided by n. This is approximation. This is the approximation. Are you with me? For beyond some value of k, after for some I greater than or equal to k, mu I minus mu k value, it will be less than or equal to some epsilon, for some small epsilon. Okay, kind of. And let's say this is the point thing, and the other point is, let's say if you're going, there is one problem, treasure hunt problem. Okay, treasure hunt problem, you have to tell the variance of some big file to get some to get the clue for the next. So there is this one guy who tries to get the exact computation of the variance by going through the whole data twice, but he loses out big on time. But there is another guy, who uses this strategy, and he will just do it not twice as fast, and and he'll get the next clue easily and perhaps win the treasure. Yeah, accuracy for large data, it's not, it doesn't matter. So in order to give you an idea, so there is one interesting, so last week, I moved the class from Friday to Saturday for a reason. I'll tell you the reason now. Maybe what I learned there will help you here. Lecture. What everyone should know. Okay, so yeah, why Why we are making a big fuss? Yeah, so this one you should see. What every computer scientist should know about latency. See, later on in your course, you will study about caches, etc. But if you see main memory reference, that is, if the data is present in the main memory, you spend the time required to access a data that is present in main memory is 100 nanoseconds. But on the contrary, if the data is present in the hard disk, okay, then what happens is the amount of time required is how many times? 10 to 4, 5, 6. No, approximately 10 power 6 times difference, times memory access. Time difference between accessing a memory and the disk is 10 power 6 x difference, million times difference. So they say, so it's not, we will not be able to quite appreciate what this difference means is. So there is what is called as a humanized difference. Like for example, if the time required to access your data which is present in the main memory, if it is equivalent to brushing your teeth, then time required to access, where is it? Disk. Time required to access 1 MB of data from the disk is 1 semester time. Okay, so that's the difference between time. If you compare the scale, brushing your teeth versus the whole semester, so that is the magnitude of difference between, order difference between accessing main memory and a disk. So now, what is the why we are worried about streaming computation? Now remember, now recall 1 terabyte of data. If you want to access it twice, then it's like 2 semesters of time or 3 semesters of time equivalent. Versus if you just do it in one single shot using streaming computation, but what you trade off is a small degree of accuracy you will trade off, but you save on big time. If you brush non-stop, right, Aniket? Okay, so Aniket, can you come on video once? We'll all wish you pranams. You'll grind your teeth and you will become old. Aniket, should all demand this. And also how much paste you require. You don't require paste because your teeth are already gone. Is there? Huh? Let's see, where is Aniket? He showed, I missed it. Come on, man, please come again. Where is Aniket? Yeah, Aniket. Yeah, hello, Aniket. Nice. So everyone can check Aniket's teeth so that we will see if the teeth will be there or not after 6 months when he comes to campus again. Thank you, Aniket. Just pulling your leg. Good. Okay. Pulling your teeth. Pulling your leg. I was supposed to say pulling your leg. I said pulling your teeth. But it came out contextually. Not bad. Okay, so much for. All right, sir. Okay, okay. So now you understood, right? Why we are worried about accessing data on the disk. We don't want to keep accessing data on the disk again and again because it's very expensive, super expensive. And in the next week, we will study on how to access data on the disk. That will be the theme for the next week. Similarly, the next challenge problem is also very similar. Okay, so now done, na? It's all. You will be able to do this in 4 days. You should be able to do this. Yeah, 2 days for the first section 1, 2 days for section 2. Yeah, I'm just kidding, but approximately in a week, you can say. What is Taurus? Taraskar, Pitiya. Oh, okay. Taras, okay. So. See, by this time you almost get the unlimited indefinite time for all practical purposes, you are getting, there are no deadlines for your assignments. So I'm just trying to say, no, it's not too difficult. That's what I meant. Not exactly 4 days. But I guess you should be able to do it. You just sit and you'll do it. What is that for JC treat? Juice canteen. Oh, Hindi and juice canteen. It's a good trade-off. No? I'll teach you C, you teach me Hindi. So, really? Gaurav? Okay. Watch CID. Punjabi is also nice. First get me Hindi. Na? Awesome. I'm looking forward. Hey, Telugu. I can teach Telugu. We'll do by having Haldiram Bhuji. Okay. Kannada for Telugu. Okay. Nice, Gaurav. So Gaurav is going to teach me Hindi. I will remember. And for Aloo Bhujia. Kushi will teach Punjabi. First get. Okay, last crypto problem. Okay. The way crypto works. Yeah, it is supposed to be this way only. So you start with a sequence, you start with a seed. Look at this one. You start with a seed, this seed somehow you generate x1 to x127, and x128 is x1 exclusive ORed with when I is equal to 127, what do you get? I is equal to 128. Yeah, so anyway, so you exclusive or this bit and this bit, and you get the bit x128, and then again x129 you get by exclusive ORing x2 and x128, like that you keep generating. You understood what is happening, right? Basically it's you just keep you keep two fingers and you keep moving your two fingers, and whatever the two bits your fingers are pointing to right now, you take an exclusive OR of them and generate the current bit. Yeah, that's true. We just need to maintain 128 bits at a time, and we output the newly generated bits. Okay. So now the question is, if this sequence is a truly random sequence, let's say you generate some million bits like this. If it's a, we think it's a truly, we start with a random seed and we keep generating like this. And if this is a truly random sequence, then if you count the total number of zeros and ones, approximately they should be the same, right? Yes or no? You start with a random seed and you keep moving like that. Okay. So what I'm saying is you start with a random. So you start with a random seed. Okay. This is a random seed. And then what happens is you get the next bit. How do you get next bit rhythm? Your fingers are pointing to this one, left finger and right finger. So you exclusive OR the left finger and right finger, and then you move one step ahead, and then you do the exclusive OR of the left and right, so on and so forth. So that is how you compute the whole sequence, let's say xn. So we don't call this as a random sequence. We call it as a pseudo-random sequence because if you see the amount of randomness that is present in this sequence, it is maximum of 128 bits. Because everything else is generated from this 128 bits, right? Yes or no? Are you all with me? Approximately. This is called a pseudo random sequence. Because we started with 128 bits. Those are, let's say, truly random bits, but we are kind of, it is very hard to define some intuitive notion of randomness. Because if you want to, can you describe this whole n string using 128 bits? You will be able to, right? So if it is truly random sequence, now you have to remember everything, right? Yes or no? If someone gives a truly random thing, if it is 1 1 1 1 1 1 1, then it's not, you just remember one followed by something. But if it is really truly random, then you have to remember everything. So in that sense, if something is truly random, then you have to remember the whole thing. But here these n bits are not truly random, because if you know the first 128 bits, then everything else you can compute. I'm just giving some hand waving things, but some intuition. Maybe perhaps later when you learn about these things more accurately, you may curse me, but for the time being, yes, the first 128 bits, or you can think of them as truly random bits, and everything else is an extension. Well, in any case, let's say if this whole is a truly random sequence, then each bit should be present 50% of the time, right? The probability is 50%. Do you see what is the problem? This is compute the probability distribution of zeros and ones here. Are you all with me? That is, you just count the number of zeros and number of ones. If this is whole thing is truly random, approximately 50% of them will be zeros and 50% will be ones approximately. And not only that, if it is truly random, the probability that the next bit is zero, given the current bit is equal to zero, you should not be able to say anything about it. You should not be able to predict the next bit. Okay, are you with me here again? If it is truly random, by looking at the current bit, you should not be able to say what's the next bit. And that's what we are trying to check here. Hey, if the current bit is zero, can I say, like with 80% probability it is zero, then it's not a good thing. Then we are not working with a good pseudo random generator. Are you with me here? These 2 points, very interesting points. That if it's a truly random sequence based on the current bit, you should not be able to tell what's the next bit is. Not only that, you should not be able to tell what is the probability that xi is equal to 0 given xi minus 1 to xi minus k. Given this, you should not be able to tell xi is equal xi is equal to 0. Problem B asks only for x minus 1, but generally speaking, if you are able to see a sequence and be able to say, that the next bit will be equal to 0, then again it's not a truly random sequence. What we are trying to get is through these A, B, things like that, we are trying to get some measure of randomness of the generated sequence. Rand percent 2 is, you generally every time you keep generating x1 by you generate a random number and you take percent 2, you generate 0 or 1. So x1, so like that, every time you use this rand percent 2, you generate this. No. Okay, let's take one step back. Okay, let's take one step back. First one, let's see, first point. From this seed, we start with the seed and we generate till xn. This computation, are you fine with this computation using this function? After we generate this, we want to get some idea whether the sequence that we have generated, if it is random or not. And we want to use different notions of randomness. Okay, for example, this is not a complete set. If this sequence is a random sequence, how many zeros will be present approximately? If x1 to xn, if it's a random sequence, if it's a truly, approximately half, right? And that's what we are trying to do here. Compute the probability distribution of zeros and ones here. Are you okay with this one? And what we are telling is this rand percent 2 approach is the rand function gives you some random integer every time you call rand. And when you take percent 2, remainder 2, it gives 0 or 1. That is an alternate way of generating a sequence of random numbers. Are you with me here? So what we are doing is there are two ways of doing it, method M1, method M2. Method M2 is this. Think of this as method M2. And method M1 is what we are looking here. So zeros and ones, approximately whichever is closer to uniform distribution, we can say, like that is kind of better. Does it make sense? That's what, compare this probability distribution. Perhaps this could be 0.6, 0.4. This could be maybe 0.51 and 0.49. Who knows? We don't know. Does 5A make sense? Are you all with me on 5A? Next. The second measure of randomness is, like, for example, if it's all 1, 1, 1, 0, 0, 0, 0, is this a random sequence? No, no. So we want to say that the probability xi is equal to 0 given current bit xi minus 1. Okay. This probability also we should not be able to say, one, if you see the current bit is equal to 0, there is something here. And if you see the current bit is equal to 0, the next bit we should not be able to predict if it's a truly random sequence. Yes or no? That means there is no, we want to avoid patterns. So that's what we are trying to compute. What is the probability xi is equal to 0 given xi minus 1 is equal to 0. But the bigger thing is, by looking at a window of k also, we should not be able to say what is the next bit is, just not a window of 1. By looking at the past k bits, we should not be able to predict the next bit. Does it make sense? But that test we are not doing here, but that's the thing. Okay, by looking at the past, we should not be able to predict. Then we say it's a truly random sequence. Are you with me? Kind of. This part we are not looking, this k bits. Right now we are just looking at this part. So why this is important is, we want to make this sequence unpredictable. If the sequence is truly random, then we can take a message. Let's say you want to transmit a message 10001110. This is the message that you want to transmit. So historically, so with the story here is, so there is Alice here and there is Bob. So they want to transmit n bits. They want to transmit, and in order to transmit n bits, what do? You just you send via some other secret channel through pigeon. Through pigeon, you send a key. You send the seed. This is seed you send. Then what happens is Alice can generate this random sequence from the seed, and it encrypts, it exclusive ORs the data with the pseudo random sequence, and it sends the data here. Why can't Bob meet Alice in person? They are not as jobless as us, so they want to communicate fast. So yeah, so that's, so they want to, they don't want to spread COVID. Yeah, that's true. Yeah, so what may be the reason? So it's like this, when you are on Zoom, let's see, if your communication between you and me, it has to be encrypted, then how is it possible? Okay, we can meet, but if you want to do a Zoom, then so we share the seed, the secret, and then we generate the rest of the sequence. Okay, anyway, so this has the pseudo-random generators and all this framework, it has a lot of applications in cryptography. Okay, so I want to learn I want you to learn a little bit about cryptography here. So that's the reason: distributions, cryptography, pseudo-random sequences. I want to learn, you all to learn a bit about it. Make sense? Are you all right with it? How will we share the seed itself securely? Good question. There is what is called as a public key cryptography. You will learn, it's a very, there's a different mechanism to share the seed using public key cryptography mechanism. RSA, yeah. I will not be teaching you because it's you learn in some other course. There is a course on this here. Not discrete structures. There is a cryptographic principles of information security. There is one course. You will learn in that course. We have a really good crypto group in IIIT. So challenge problem, implement RSA. Go ahead, one challenge yourselves. Okay. Nice. So this problem, you should again be able to do it in a couple of days. Yeah, you will get A grade in if you solve permanent in polynomial time, then you will get A grade in C programming course. Okay, so problem 4 is on how to work with the data on the disk. So write a program to compute the combined character frequency. So you are given, like for example, 100 files of data, Wikipedia pages, and you compute the frequency of different characters. Thesis over in first year. If you solve permanent in 1 year, you don't need to worry about thesis. You'll directly become professor in MIT or something like that. So, anyways. Write a program to compute combined character frequency means, it's just not learn the character frequency per file. You look at all the files and compute the frequency. Write a program to compute the combined word frequency. This is a slightly more challenging problem than before. And here comes the performance. Yeah, sixth one is linear traversal. Seventh one is bit challenging. You have to work hard. And this is the place where I wanted to give a performance contest. So there are two big files. Let's say one file is 40 GB, another file is 60 GB, and both contains sorted list of names. You have to create an output file which contains the list, all the names from both the files, but in the sorted order. And 4 does fastest program. There's something good, get good gift from me. Yeah, you do merging, but how do you do? Yeah. This is going to be a fun problem. Problem 8, super fun. Problem 9 is super fun. Good. No, we will give a program to generate a 50 GB file. Okay, and then problem, you will get couple of interesting problems from genome sequence analysis. Yeah, last two problems. Okay, so that is about the homework. I think you got a good picture on the problems, I guess. Okay, let me stop recording.